audience is Bill Nazaroff, who was our advisory chair. So we were the core conference group putting this together. If anything goes wrong, it's my fault probably, so let me know if you need anything. So basically the summer school is just going to consist of 2 days. As you know, we're going to have some nice lectures by people like Andy Persily, Bill Nazaroff, and some other people that are going to show up later. You've seen the schedule, so I'm not going to run through it just in detail. We're going to have 2 more breaks today. We're going to have a lunch break in the same area, as well as a refreshment break in the afternoon in the same area. And tonight we're going to be having dinner and sightseeing, but that's really turning into just dinner and taking taxis in the rain over there, something like that. So if you don't know yet, we're probably supposed to have a bad storm tonight. So we're going to be at 3925 Walnut Street. We'll talk about this after the day concludes. We'll all head over there together. We have a nice area reserved with free food and things like that, so we can all just socialize and hang out. Then tomorrow we'll be back at 9 to finish up the summer school, and it concludes at 4 o'clock. Registration starts at Drexel at 3:30, but if you've checked in, you are all already registered for the conference. You don't need to do anything else. This badge is for the conference as well, so please bring it. We will be giving you an email later today that's going to have 2 pieces of information. One is Bill Nazaroff has put together a series of references for his talk, so we're going to email out his reference list. And the other is going to be a Dropbox link to all the conference proceedings. Okay, so we have USBs, but we had a little bit of hiccup with the delivery where only 2/3 of them were delivered. So we're just kind of holding on to them right now and waiting for the rest to come in. So as summer school attendees, you are going to help us out a little bit at first. And you're going to start with a link, direct link to a Dropbox folder, and then as the USBs come in, if you want them, we'll make sure you have them. But it's the exact same information, so, you know, it's just another piece of electronic trash, really, okay? And then tomorrow at Drexel, we have a opening reception that starts at 6:30, okay? And that'll be in the great court in the main building, and so we can talk through that tomorrow if you have questions. And then, that's the opening ceremony at 6:30 to 7:30, and then the opening reception is at Drexel right after that in the same area from 7:30 to 9. So we'll have food and drinks. Please plan on staying around. If you know people are coming to the conference, encourage them to come so we can all hang out before everything starts for real on Monday at the Convention Center, which is where the technical program will be for the next 5 days of the conference. Okay? Anyone have any questions about anything? Yes?
Will the Dropbox link also contain slides for today?
So it does not. Unfortunately, we were not able to give out slides because of copyright issues, but what we are doing is we're going to be screen recording all of the lectures and voice recording, and so we're going to put those up on the ISIAQ website once we get them all in order. So you will be able to see the slides again, but we're not able to actually pass out physical copies. Okay? So it'll be available a bit later. Some people will be writing on the board. We encourage you to take notes, of course. We've got these nice sort of desks that are good for that. But that's it. Any more questions? Okay, so the school today is not going to be run by us. Yes, go ahead.
A couple other people.
Sure, I'm sure I forgot something.
If anyone needs Wi-Fi.
Okay, right. If anyone wants Wi-Fi, go to the Drexel or just open up your networks. Drexel Guest is what you want. You don't need a password. You just put in your email and accept the terms, and you can have free Wi-Fi the whole time you're on campus. At the Convention Center, that'll be different, but we'll have the SSID and the password there. Okay? What was your second thing?
And then the other thing is, if you need any help throughout the next 2 days and into the conference, if you see people with an orange sticker on their badge, they're official organizers.
Yep.
Most students and staff, mostly from Drexel and IIT. And so maybe anyone, so you've got those here, Brian in the back.
Raise your hand if you're a student helper from Drexel or IIT. Good, so we're all over, okay? So ask anyone if you need help.
Good.
All right, good. Okay, so Brent and I are not going to be running the school today. We'll come back for lunch and refreshments, but we've got to, of course, get some other conference stuff organized. The MC today is going to be Pratik Pant, who's a student of mine, and then Chun-Yi Wong is also a student of mine, and he'll be helping all the presenters get their presentations loaded, as well as start the screen recording. Okay? So, if anything else before we step it up and turn it over to Pratik? Okay, well, we'll be back, and we really hope you enjoy it. We're glad you're all here. Okay, thanks. Oh, one more thing. If you tweet, here's the hashtag for the whole conference. Publicize everything, take pictures, take lots of pictures of Andy Persily. It's going to make lots of jokes, ask him hard questions. We'll be back.
All right, welcome everybody. Let's begin with the 10:30. It's on ventilation by Dr. Andrew Persily.
Yeah.
Yes, go ahead.
Great, thanks very much. Is there a microphone I need to worry about?
It's actually
or-
on. Yeah.
Okay.
It is.
Well, good morning. Nice to see you all. This is school on a Saturday morning. It's like the movie The Breakfast Club. Oh, good, some of you have seen that. Yeah. I don't know what you did wrong to be assigned to the Saturday morning school, but hopefully at the end of this, you'll have done your penance and be able to move on with your lives. You're in for a real treat this weekend. Several of us spoke at or attended the summer school 2 years ago in Ghent. And it's a great opportunity for you all to get to know each other and socialize and talk about your work and your careers. And then as the week goes on, you'll be, bumping into each other. So, this is a great opportunity. Take advantage of it. So welcome and good morning. I'm talking about ventilation today, and I'm going to tell you everything I've learned over the last 40 years in 90 minutes. And actually, I really only need about an hour to tell you everything I learned, but the schedule is the schedule, so I'm going to take 90 minutes. Everybody's on Wi-Fi, right? So you can go do something during the slow times. I have my email address and phone if you ever want to contact me and ask me a question. I can send you my slides. Drexel cannot copyright them because I work for the federal government, so I can send them to you. So feel free to ask. The other thing is tomorrow, Ellison Carter from Colorado State University and I have a session on giving an effective presentation. So unfortunately, my presentation is not going to be as effective as it would be after tomorrow's session. So this will kind of be one extreme and tomorrow will be different. So enough of that. So speaking of effective presentations, I find it very helpful to create an outline of what I'm going to talk about. And when I do this, I actually write down the number of minutes I'm going to use, and then I take it off. But I figured I'd leave it up for you, as maybe something you find useful. So these are all the things I'm going to talk about and how many minutes I think it's going to take. So, use that little tool if you want to, but when you give your talk, you should take those times off because, people will wonder what the heck that's about. So what I want to start out with is to, ask you some questions. What do you want to learn about? How many people have ever seen a ventilation system? I know Alexa has. That's pretty good. And and that means, the air handler, the furnace downstairs in the basement, or it means the big air handling unit that's upstairs, I'm going to guess, in this building, but sometimes they're downstairs. And how many people have ever measured a ventilation rate in a building? Okay, you think you have. But we'll talk more about that later. So what do you want to learn about ventilation today, so I make sure I actually say something you want to know about? Don't be shy. Yeah.
Different terminologies.
Terminology. You saw that on the last slide. Okay. That terminology is really important. I had a combustion professor years ago, and he said that's all you really need to know is the terminology, and all the other stuff, it's just math. Any other things people want to know? Yeah.
Sure. You have those dual systems that operate passive ventilation and mechanical. So how do those operate with the economizer, things in that shape?
Okay. I think I'm going to get into some of that, but make sure I don't forget. I know I'm going to talk a little bit about ventilation systems, but you're pretty aware. You're more aware of. You know some good terminology. That not all. How many people know what an economizer is? Okay. An economizer is a fancy word for a system that's able to bring in a lot of outdoor air for cooling. So if it's dry and cool outside, you can cool your building with the outdoor air instead of turning on the chillers. So it's an energy efficiency mechanism. And it's called an economizer cycle. It may double, triple, even more than 5 times the amount of outdoor air that you would bring in under normal minimum operation, but it's a energy efficiency mechanism. But you don't want to do it when the air is dirty or outside or humid, because it'll mess you up. But it's a very, very common practice. It's also an operation mode that often goes out of tune. But the sensors are bad, the dampers are bad, and then it might go into economizer operation, in the middle of the summer, which you don't want. Thanks for that one. I saw another hand. Yeah.
Infiltration credit.
The infiltration credit in like standard 62 too?
Yeah.
I'm going to talk about 62.2 a little bit. I don't like their infiltration credit, but we can talk about that later on.
I recently saw some articles saying that this infiltration credit is not like very accurate, so I wanted to know a little more about that.
Sure.
Pros and like.
Yeah, I mean, that might be a side conversation, but that's we could have later on. And it's not very accurate, but accuracy is good, but there's more to life than just accuracy. But we can talk about that. Giorgio, my old friend.
How do you balance energy efficiency and indoor air quality through ventilation systems, or which ventilation system?
Okay. I can't remember if I get it. I'll talk about that a little bit. I have a whole nother talk about, I'll call it the balance or the dual goals of good indoor air quality and energy efficiency. In a lot of people's minds, you pick one or the other, but not in my mind. There's lots of things you can do to save energy and get good indoor air quality, and they don't have to be, in opposition to each other. Any other things people want to, yeah?
How does a ventilation system interact with abstract species in the system itself?
Interact with?
Say air pollutants. Say, how does that remove ozone, or how does that react with different types of, say, local organic compounds? So how would air composition be affected when it's going through a ventilation system?
It definitely happens. Some particles and reactive compounds, you lose some of them. Some of them will react with surfaces and generate other things. I'm not going to get into that in a lot of detail. I'll try to remind me if I don't, or we could talk, during a break. Bill can tell you a lot about that topic. Right?
We'll cover a little bit of it in the particles lecture later.
Well, we're going to be here all week, so let's just start the discussion today. Any other things? Yeah.
What other pollutants to be taken into consideration with the indoor air quality procedure?
Yeah, I'm not, the indoor air quality, I'm going to talk a little bit about ASHRAE standard 62.1. That's kind of the old, well, it's been around for decades. It is the, I don't know what to call it. It's a very well-known standard has ventilation requirements in commercial and institutional buildings. And it's been around since 1973. And it basically has a table of how much air you need per person or per meter squared floor area. It also, when it's like a cookbook. You just do the calculations, you decide how much outdoor air to bring in. It also has a performance method, where instead of using that table, you decide how much outdoor air you need to control contaminants. And you have to pick the contaminants, and you have to pick the levels to which you're going to design. And it's hard to do because there's not a lot of data on that. They don't say which contaminants you need to pick. They have, actually right now, out for public review, they have a new version of the indoor air quality procedure that tells you which contaminants to design to. So you should submit a comment on that public review. Anything else? Well, feel free to ask questions if you need to as I move along. These are all good questions. I'm going to get into some of these for sure. So, I make a slide that has all the times, and then I put it down on a table where there's no light, and so we'll see what happens. But at least, you know, I thought about it. So why does ventilation matter? You know, why do we care about how much air you bring into the building, how you move it around, how you get it out? Well, you know, indoor air quality for us this week, that's the most important reason. You bring in outdoor air so that any contaminants that are generated within the occupied space get diluted. But it also brings in outdoor contaminants. Anything that's in the outdoor air will come in with that ventilation air unless you have a proper filter or an air cleaner. We're pretty good at taking out particles. Ozone isn't too hard to take out, but CO is really, carbon monoxide is really hard to remove, and various organic chemicals. So most systems have particle filters to keep the coils clean, not to protect the people. You know, the only places that you commonly see serious air cleaning are like museums and semiconductor manufacturing equipment to protect things and processes. Hospital, thank you. You don't see them so much to protect, you know, office workers and students. They're all expendable. So we care about ventilation because of indoor air quality. We care about it because of energy. You bring in that air. Today you need to take some moisture out, maybe cool a little bit. In the winter you need to heat it. In some buildings they humidify, they add moisture. That's not terribly common, and it takes a lot of care because you don't want to squirt water into a ventilation system unless you give it a lot of thought. So energy is another reason. Thermal comfort is another reason ventilation. And I'm using ventilation in the most general sense. It's really any air movement, not just outdoor air. So ventilation matters because it helps with thermal comfort. I got this thing. There we go. By controlling temperature, humidity, and airspeed. And then this reminds me of, I was interviewed by Quartzy. You ever hear of Quartzy? Yeah, I didn't think, you know, it's some website that's trying to make a name for itself, putting up articles about all sorts of topical things. They interviewed me about where's the best place to put a fan in a room to keep it cool. And I made the point that those fans you put in the room aren't to cool the room, they're to cool the people. And there's no point in running the fan in the room when there's no people there. That just generates heat. I'm not sure they understood that or not. So thermal comfort is another reason. And then another reason ventilation matters is material degradation. When you bring outdoor air and moisture into a building, it may condense within the envelope and corrode metal and rot wood, and it can cause serious structural issues. You know, in cold climates, the water will get in the wall, it'll freeze, it'll expand, and big pieces of the wall will fall down on the sidewalk. That's not good. And by microbial growth, things will grow in there and rot the wood. So these are the reasons why we care about ventilation. You know, it's nice to see ventilation as the first technical subject at summer school. And maybe that's a reflection of the importance of that they're in the minds of the organizers, or they wanted to get me out of the way and move on to more important matters. But I'm gonna take the optimistic view. So that's kind of some of the reasons why ventilation matters, and I only have a few equations today, but I gotta have some. So these are the equations that tell you in a very simplified form how ventilation impacts indoor air quality and energy. So this is an overly simplified mass balance equation for the indoor concentration of a pollutant. It's the outdoor level plus what's generated inside divided by the ventilation rate, the outdoor air ventilation rate, minus any air cleaning, minus other losses, which might be deposition on surfaces and so on. I mean, life is more complicated than this equation, but it gets the concepts around. You're going to see other forms of this species balance equation as today and tomorrow go on. And then this is the energy equation. So here's the ventilation rate, the outdoor air ventilation rate. And then here's the energy equation. This is the energy required to heat the air you're bringing in. This is sensible load. We call this sensible load. At least the engineers do. And then this is the energy required to remove the moisture on a day like this. So this is called the latent load. Hopefully that means something. Plus fan energy to move the air if you have fans, and then minus any heat recovery. You know, there are these heat recovery systems that on a winter day, the outgoing air warms the incoming air through a heat exchanger of some type, and so you don't pay the entire energy penalty. And they make a lot of sense. It's another piece of equipment that has to be maintained, but it's a good thing in general. Yeah, again, I said, you know, if you have questions that you don't want to say till the end of the break, please raise your hand and I'll try to pay attention. So terminology. Remember, this is all you need to know is terminology. So this is a overly simplified representation of a ventilated space. And here's some important terms. Infiltration, I'm going to talk about this a lot. This is leakage, this is uncontrolled leakage into the ventilated space through unintentional openings in the building envelope. Okay, this is driven by wind and temperature difference between inside and out. And it's also will be driven by, if you have an exhaust fan that's pulling air out of the building, it'll drop the pressure inside, or tend to drop the pressure inside, all else being equal, and increase the infiltration rate. So this is important. Common assumption on the part of many is that, well, common is neglected. They talk about, you know, hermetically sealed office buildings, they don't exist, you know, and so that's an important one. Exfiltration is just a leakage out. So sometimes we lump the terms together. And then this is a simplification of an air handling system. So there's outdoor air coming in, and I notice I don't call it fresh air. If anyone ever says fresh air, you ask them where they live, because there are places where the outdoor air is fresh, but they're becoming less and less common. So it's outdoor air. Sometimes you call it bake-up air when you're referring to the outdoor air that is brought in to make sure the exhaust system can work. Because, you know, if your exhaust system, if there's no air coming in, the exhaust system, the fan runs, it makes noise, it uses electricity, but it doesn't move any air unless there's some air to pull. Yeah.
I wanted to ask about infiltration. Is it intentional or unintentional?
It is.
Open the windows or doors.
Infiltration is unintentional. You know, open windows, we call that natural ventilation. So infiltration is bad. It's uncontrolled, it's unconditioned, it's unfiltered. You don't know where it's coming in, you don't know where it's going. It's the cause of some of that material degradation in the envelope, moisture problems. So ideally, you don't want infiltration. You know, that doesn't mean you have to have a mechanical system. You could have a designed natural ventilation system, but infiltration is bad. The old phrase from 1980s in Sweden was build tight, ventilate right. And it's still true. So there's the outdoor air. It goes in through some kind of air conditioning system where it's heated, cooled, dehumidified, filtered, whatever is appropriate. And then we somehow call it supply air at that point. Sometimes they call this primary air, but I'm not gonna say that. And then the air coming back from the space to the mechanical system is called return air. Some of that is dumped to outside, sometimes you call that spill air, and some is recirculated. Every now and then you'll see an article about ventilation, or in the popular press, you know, it's like, oh my God, they recirculate air. Well, they recirculate air in almost every building. Every home in this country with a forced air system is only recirculated air. Low-rise residential buildings typically don't have any of this. It's all recirculated air. So recirculation isn't evil all by itself. And then you have local exhaust fans in toilets and kitchens and some other places where there are strong sources. It's better to remove the pollutant right where it's generated rather than let it get into the entire space and then, you know, let the general ventilation take it out. And in some cases, you need a local makeup for that fan to work. So there's some terminology for you. And here are definitions of all those terms. And I'm not going to read them, and you don't need to read them. And if you ask me for the slides, then you can read them. And most of these definitions come from ASHRAE Standard 62.1. But you will, the only one I'm going to point out is in here. But ventilation, you know, in some sense, all of these are ventilation. They're air movement, you know, and so it's really important, you know, to be a little precise. Talk about outdoor air. Talk about outdoor air ventilation. Talk about outdoor air outdoor air intake. Talk about supply air. You know, there are supply vents in this room over here. I don't know if there's any outdoor air in them. You'd have to go to the air handling unit and see if the damper's open. So I know that's supply air, but I don't know if there's any outdoor air in them without going to the fan that's actually moving the air.
You just essentially filter the air, and it goes through the system, and it's the same air, just filtered there.
If there's no outdoor air. You know, in some buildings, it's 100% outdoor air. There is no recirculation. You know, that's in some hospital spaces, you'll see that, and I've seen that in some libraries. But there's a big energy cost, but in some cases you need it. Here's some, yeah, here we go. Here's some other terminology, and so ventilation, this is pretty much right out of Standard 62.1, and all it is a process of supplying and removing air naturally or mechanically. Naturally is driven by weather, mechanically is driven by a fan of some type. And when you read the definition of Standard 62.1, it never says if it's outdoor air or not, which is fine, but when you use the term, you know, you want to be a little more precise. I don't know why I'm pointing to my head. I'm pointing to my mouth. But you want to say, is it outdoor air ventilation? Is it supply air ventilation? Otherwise, I don't know where it is, where it came from. Natural ventilation, that's the outdoor air coming into a building intentionally through intentional openings. Windows, doors, non-powered vents. You are seeing more and more sophisticated natural ventilation systems around the world, including some very, very tall buildings in Asia where they're doing some really clever things, you know, looking at the weather patterns and deciding where to put the openings. There's certain advantages to natural ventilation, you know, less energy, maybe more air, connection to the outdoors, that's all good. If the outdoor air is dirty and moist, it's not such a good thing. A lot of these systems are designed by architects based on aesthetics and wishful thinking, okay? We know the engineering principles by which natural ventilation systems can be designed, and we have tools to do that, you know, and we understand the physics. You really need to do the engineering analysis to decide how big to make the openings and where to put them and how much air you're going to get. You know, the air doesn't look at the drawings that the architect makes and sees that I'm supposed to go from here to here. You know, air can't read or look at pictures. You know, the air goes where the lower pressure is, regardless of what the drawings say.
Are there any heating or cooling provisions that limit how much we use the return air to mix with the?
Yeah, I mean, we could talk about that more later on, but when they size the heating and cooling system, you know, they look at how much heating do they need on a cold day and how much cooling they need on a hot day, and kind of the airflows associated with that and how much recirculation is happening as part of that load analysis. That's the short answer. Mechanical ventilation, that's the air brought in, or the ventilation, that's the air brought in through a fan. Might have ductwork and might not have ductwork. Transfer air is air moving from one space to another. You'll see that a lot of restroom doors have grills in them so that the exhaust fan can pull the air out of the restroom, and then air from the hallway can come in. That's called transfer air. And then air tightness. That's air leakage in the building envelope. That's a physical characteristic of the building envelope how leaky it is. And you measure that with a blower door test or some other type of fan pressurization test where you impose a pressure on the building and measure how much air you need to raise the pressure inside. Anyone familiar with blower door tests? That's another talk. And I don't think I have a slide on that. And then the air change rate, that's really, in some sense, it's a unit. It's a flow rate, an airflow rate in liters per second, or CFM if you must, of supply air or outdoor air divided by the volume. So it's really just a unit, often expressed in air changes an hour. But all by itself, an air change rate, I don't know what it is. Is it supply air? Is it outdoor air? I think I've made that point enough. And I said liters per second because I'm bound by law to use SI units. So I'll try to stick with that. Okay, so here's a few important concepts. If you get nothing else out of this, the envelope infiltration rates, the leakage, are impacted by weather. I'm going to show some data later on. A 5-to-1 variation, 10-to-1 variation in a given building is not uncommon, depending on how cold it is and how windy it is. Ventilation system, the rates moved by a ventilation system are not constant. They're not designed to be constant. They're controlled, hopefully, and they're operated depending on season and weather condition. We have the economizer, in some commercial buildings that really bumps up the outdoor air intake when it's cool and dry. You might do that in a morning, maybe not today because it was kind of humid, but ventilation rates aren't constant either, and I'm pretty sure I'm going to show you some of that data. And then buildings are not tight unless they're built that way. Do not assume they're tight. To a first order magnitude, the infiltration rate in a building is going to be equal to what the system brings in. And look at me, I wrote ventilation rates and I didn't say outdoor air ventilation rates. Shame on me. But to the first order magnitude in buildings, the infiltration is the same as what the system's bringing in. And it's not tight unless you measure it and can convince yourself that it's tight. We have a house, a net zero energy house on our campus that we've been studying, and it's one of the tightest houses in North America, but it still leaks. And the infiltration rates in that house are about a third of what the mechanical ventilation system bring in. In part, it's because the mechanical ventilation systems are so low because it complies with standard 62.2, but that's a different discussion.
Do you have to measure the infiltration rate in the States, or is there a time?
It's not the air tightness, the blower door test. It is becoming more common. There may be a couple of states that actually have a requirement, but it's not very common. But more and more builders are doing it because they understand the advantages of having a tight building. I mean, when I started in this field all those years ago, every house in Sweden had a blower door test. And if it means anything to you, it had to be 2 air changes an hour at 50 Pascal. But not so common in the U.S. Oh yeah, 1 air change an hour. These are all these things that I just need to kind of get off my chest towards the beginning. And then I can relax, and you can relax. But 1 air change an hour does not mean that all the air in the building is gone in an hour. It's just that basically one building volume of air enters every hour, but as it comes in, it mixes. So at the end of the hour, there's some air that was there at the beginning of the hour, there's some air that was there yesterday. So it's just a unit where you're taking the amount of air entering the building divided by the volume, and it happens to be 1. So it doesn't mean it's all replaced. You probably didn't think that anyway. ACH is not a unit. Okay, whenever I review a paper and I see someone use ACH as a unit, I make a comment. First comment is, doesn't this journal have an SI policy? If it's strictly SI, it would be inverse seconds. But, you can get away with inverse hours. So don't use ACH. Or just don't use it and talk to me about it, but it still bugs me. And then another thing is I really don't like the term air exchange rate. And for a while I just didn't like it, and now I've thought about why I don't like it. And it's because it kind of gives you the impression that it's just a simple exchange between inside and outside. The inside air is exchanged, but in reality it's more complicated than that. In a house, air might enter through a crawl space, go into some kind of plumbing, a chase where plumbing pipes are, then go into the building, then go into the attic, and then go outside. Or it might go into a wall and move up the wall and then into the floor of the second floor and then come in. It's more complicated than that. So, at some point in your life, you start to be able to allow yourself to get upset about things. And later on, you've got to get to a point in your life where you don't get upset about them. But I don't like that term. But that's, that's me. That's me, and that's my opinion. And we can talk about that another time, too. So here are some important concepts to keep in mind and try to remember if you don't remember anything else. Again, you don't have to write all this down because I can send you these slides regardless of what Persily University says. So how do you characterize ventilation? What parameters are relevant? I've referred to a lot of these already. One is the whole building outdoor air exchange rate. This is the volumetric rate at which air enters the building from outside. Sometimes you care about the room outdoor air change rate. That can be much harder to measure. If it comes directly from outside through the wall, well, that's hard to measure too. But some outdoor air goes to this room and then goes into your room. So those concepts, a lot of what we're talking about, we're treating the building as a single volume. And no, that's much more straightforward. You get to multi-zone buildings like this one and pretty much every one. It gets a little more complicated. Room air change rates are harder to think about or harder to quantify and define. You can take the supply air coming into this room, divided by the volume, and you can get the supply air change rate of this room, and you can find out what's the percentage of outdoor air in that vent, and then get the outdoor air, the mechanical ventilation outdoor air change rate of this room. But outdoor air may be coming in through other walls. I don't think we have any outdoor walls here. But we're in some sense, we're getting the outdoor air that's coming into this room from that zone. How do you quantify that is real challenging. So there are the outdoor air change rates we care a lot about because they dilute the internally generated contaminants. And then there's all these airflow rates in the ventilation system, the supply air, the outdoor air, and the exhaust. I'll talk about how to measure those. The infiltration rates. This is the amount of air that's leaking in through the walls under the given conditions. And then the building air tightness. This is a physical measure of the air tightness of the building. You can measure this in like an hour or something if you're, you can measure it in an hour. Measuring air infiltration rates, since they're time dependent and weather dependent, you can measure these forever. And then just, quantify the variation, and I'll show you some of the variations. So this is the actual air leaking through the walls under natural conditions induced by weather. This is a physical characteristic of the envelope that doesn't change, in quotes. Some people have done blower door tests in a house like every week for a year, and it will change. I did that about 50 miles from here a long time ago, and in the summer, when it got humid, the wood would swell and the house got a little tighter, and then in the winter, the wood dried and shrunk and the house got a little leakier. But that was like a 10% effect. These measurements aren't a lot better than 10%. So here are 4 parameters: outdoor air change rate, ventilation system airflow rate, infiltration rate, and building air tightness. All of them are important to varying degrees depending on what you're looking at. So I talked about this already, didn't I? This is a little more information on the building air change rate. So it's you can think of it as the total outdoor air entering a building, which is infiltration plus the intentional intake from the system. It's both. You can separate them, if you measure the total with a tracer test, and then you measure the intentional through the system, you can get the infiltration by subtraction. It hasn't been done in very many buildings, but it has been done. You can measure the outdoor air change rate with tracer gas dilution. I trust many of you have heard about tracer gas techniques. There's an ASTM standard, E741. There's an ISO standard also that I really ought to list here for the benefit of generality. And there are basically three techniques: decay, where you put in the tracer gas, you let it mix, and you measure the decay rate over time, and then I'll show that. Constant concentration, where you inject it and you have a feedback loop, and basically the controls and modulate the amount of tracer you inject to maintain the concentration at a constant level. And then constant injection, where you just inject the tracer at a constant rate and then see where it ends up. And they all have advantages and disadvantages, and we'll talk about some of those later on. Typically, these are single zone approaches. I mean, if you look at the ASTM standard E741, I'm pretty sure single zone is in the title. And that means that you're assuming that the entire building is at the same tracer concentration, which in some cases is a great assumption, and in some cases it's not so great. And if it's not a uniform concentration, I think within 10%, these techniques and the math behind them kind of falls apart. So you gotta, if you're going to use a single zone technique, you need to verify that your concentration is sufficiently uniform. I'm just going to talk about that. Throwing some tracer gas into a bedroom and and then monitoring decay while you ignore the rest of the house is not necessarily meaningful. You will get a decay rate, because it will decay, but you're ignoring, what's the interaction with the rest of the house. So you're not necessarily going to get an outdoor air change rate for that room. It's a lot easier, but you're using a single zone. If you write down the math for the tracer gas balance, you've got to include the other rooms. And if you're not measuring them and they're at different concentrations and they're connected with airflow, this doesn't work. There are tracer techniques that account for multi-zone effects in buildings, and they're more complicated. Some of the single-zone tracer gas techniques you could almost do on a routine basis. These are more in the realm of research, which in some sense makes them more interesting and more fun, but it's a lot of work. It's also very difficult to measure air change rates in naturally ventilated buildings. And I have not seen a lot of measurements that I have great faith in. I'm behind in my reading, so I might have missed some papers where they just nailed it. But if you think about, here's a wall with an open window and air's coming in, you're going to have a lower tracer concentration where that air is coming in. It's going to be hard to get a uniform tracer concentration in a naturally ventilated building. There's some other things you can do, but it's tough. It's tough to measure that. So a little bit about tracer gas decay measurements. This is an automated tracer gas system that we used in one of our test house. It injects tracer every few hours, and then it measures the concentration at multiple locations in the building, and it measures it outside, which is a good thing to do, because if you're getting a high tracer concentration outside, something's probably wrong. And it's there's just a single zone mass balance for the tracer gas in the building. You're assuming, after the injection that the generation rate is 0 and the outdoor concentration is 0, and then this is the equation where the rate of change of concentration times the volume of the space is just the ventilation rate, or in volumetric units times the concentration, and you can solve it for a constant value of ventilation, and it's just the concentration decays exponentially, and if you take a log of everything, it's just you plot the log concentration, you should get a straight line, and it slopes the air change rate, and that's how you do it. And people done any tracer gas decay measurements? And a few people here. So hopefully this looks familiar. It's not too complicated. One of the keys is that you are assuming that the concentration is uniform again. And that's why we measure it in different rooms. Now this house is kind of weird because it had a crawl space. And, you know, with ductwork in it that leaked. So some of our tracer went into that crawl space, and that's a whole other discussion how we dealt with that. And, you know, but you're assuming that it's uniform concentration, so whenever you make an assumption, you need to verify that your assumption is valid. That goes for everything, not just tracer tests. So that's decay measurements. This is not a new technique. Every now and then I'll get a paper to review from someone who's rediscovered the tracer gas decay technique. And usually they're from industrial hygiene journals. And I reply, reject. And I sent them this paper from 1934, 35. There's an older reference in German, and I can't find it, because I'm going to send them that one. It's maybe early 30s or something. So people have been doing decay tests for a long, long time. And so it's good to know, it's good to read the literature. The constant injection technique. This is where you inject the tracer at a constant rate and you measure you inject the tracer at a constant rate into the space and you measure the concentration response. And you do the same single zone mass balance. So here's the equation. The rate of change of concentration times volume is what you lose through ventilation plus the generation rate. And you can solve for Q, and you can integrate both sides. And this is the technique that's behind long-term PFT measurements. Anyone ever run into PFT measurements? For a lot of times you read about this and they'll say we use the PFT technique. Well, PFT is perfluorocarbon tracer. It's not a technique, it's a substance. The technique is a long-term average constant injection technique. And this is the equation. And the thing is, at steady state, you can use this equation to get an estimate of the average air change rate, which is just the generation rate times the average of 1 over the concentration. Well, I wouldn't call it a problem. There's an issue here that the average of the inverse concentration is not the inverse of the average concentration. Okay? The technique measures the average concentration, they invert it and assume it's the same. So there's an inherent bias in this technique, which overestimates the air change rate. It's well documented, not always appreciated by people who do it. But since you have a lot of experience with it, don't worry so much. If you let this go out to steady state, then the ventilation rate is the generation rate divided by the steady state concentration. And this is the basis of using occupant-generated CO2 to estimate ventilation rates. Is that something anyone here is familiar with, using CO2 in this manner? I think that's the next slide. Oh, yeah. No, it's not, but it's coming up. This is real common. A lot of the people who use peak CO2 to estimate ventilation rate don't know that they're doing a tracer gas test within a well-established technique. And well-established assumptions behind the technique. They just do it. You shouldn't just do things. You should understand things and then do them. I mentioned the airflows and ventilation systems. You want to know how much is moving through that duct. You want to know how much is moving through that vent. You want to know how much is moving through the outdoor air intake. And people have been measuring these flows for a long, long time. There are standard techniques. They use pitot tubes. Anybody know pitot tube? Old school, huh? Or hot wire anemometers. And you put them in the duct and you move it around to get an average airspeed. You multiply it by the area of the cross-sectional area of the duct, and now you have a flow rate through the duct. It requires that the velocity profile has a certain amount of uniformity across there. But in a lot of ducts, you don't have that, and there's swirl and all sorts of crazy things going on, which can compromise the accuracy. If you look at the standards, like ASHRAE Standard 111, that describe these techniques, I think it says it's plus or minus 10% under good conditions. They don't describe good conditions. I don't know where they got the 10% from. You know, I think it was like if they said it was 5%, nobody would believe them. And if they said it was 20%, nobody would use it. So I think that's how they got the number. But I've looked, I have never seen anything, and that's, you know, you don't see, you know, where they measure it in a duct there's tracer techniques you can use here to measure these. Oh yeah, tracer gas and ducts. There's an ASTM standard for doing that. And that's becoming more and more common in stationary power plants and the stacks, where they have to monitor the pollutant being, you know, released to the outdoors through a coal plant or some other plant. They'll use a tracer gas. They'll inject tracer at the bottom, let it mix, and measure the concentration at the top. They do that at the Fire Research Lab down the road from us. Outdoor air intake ducts are usually really short and really hard to measure. You don't get the profile, the velocity profile to do this, so it's really hard to do. What you can do is measure the supply duct downstream, the supply air downstream, and then estimate the percent outdoor air, you know, in the supply air with the tracer gas or using temperature. You can measure ventilation into and out of rooms through supply vents, through exhaust, and so on, with a flow hood, which is a commercial device. There's questions about the accuracy of these. If you do this all day long, your arms will get tired. Okay? Office buildings, they will do it. They go to every vent, you know, they establish it, they adjust dampers, and they will, you know, because part of the design of a mechanical ventilation system is how much air is going to come out of every vent. So they go and check, supposedly. They definitely submit an invoice. But they check, but if you ever, they call it testing and balancing. If you ever look at a testing and balancing report, they'll have a list of all the supply dampers, the design flow, and all the measurements. And it is astounding how closely they match. You know, I would just, if it's 100 design, I would put in 95, I put in 105, but it's almost exactly right on there. And you know that can't be right. But that's how they do it with these flow hoods, which you can buy. And they're, you know, if you want to, you're doing a study of a residential building, that's a good way to measure what's going on in the kitchen exhaust. But, and there are smaller ones for smaller flows. But that's kind of the standard technique. But I don't have a ton of faith in the accuracy, but I don't know any other way to measure it. A point that I may forget to mention later, is in some of these flows, and you're trying to understand the dynamics of what's happening in the ventilation system, it's really helpful to measure it more than one way. You know, measure the intake if you can traverse it. Measure the supply and multiply it by the percent of outdoor air. Measure it in multiple ways, and hopefully you're going to get some level of consistency. It'll give you a sense of how much faith to have in the numbers. So there's a message. Measuring something one way is where you're not so sure the accuracy can get you into trouble. Oh, infiltration and airtightness, I talked about this already. The infiltration is the airflow through the leaks that happens because the wind's blowing, because it's colder outside. And I think I've said all this, you know. If you have a mechanical system, you can measure the whole building air change rate with the tracer gas, and then subtract off the outdoor air intake rate that you measure with the traverse. In the U.S. anyway, infiltration rates are the same order of magnitude of intake, unless you measure them both and conventionally otherwise. And then air tightness is the physical air tightness of the envelope you measure with the blower door, or in a big building, you bring a big fan. And this is becoming more common in commercial buildings than it ever was before. Yeah, so there you go on there. So, some more questions for you. I might have asked how many people have done tracer techniques of some sort, and you checked all your assumptions, right? Okay, not a lot of hands. And so the best way to measure ventilation, I get this question a lot. How should I measure ventilation in the school I study? And Well, yeah, I'll ask you first. Anyone have an answer, the best way to measure
Andy,
ventilation?
can I, because I've been thinking about this during your presentation, I ask you, especially at this point, to differentiate between residential, single-family dwellings, let's say especially, and larger buildings, when
Sure.
we're thinking about ventilation.
I mean, in this country, anyway, low-rise residential buildings are almost exclusively ventilated by infiltration, by leaking, weather-driven leakage in the walls.
Plus natural ventilation.
Plus natural ventilation, open windows, open doors. But the studies that have been done of window opening patterns show that people don't open them a lot. It's a noise issue, it's a security issue. So, the few studies of window opening patterns show that. And they often have local exhausts. They're required by building regulations of local exhausts in kitchens and bathrooms of a certain amount. Typically, the fans they use are not very good, and they don't move very much air. Unless, you can buy a good kitchen exhaust fan, but the ones that are used, kind of the builder grade, they might call it, once they're installed and there's duct work, they might move half of what they're rated to move. So on the residential side, low-rise residential in this country, you have infiltration, some natural ventilation, and hopefully some local exhaust. You have some low-rise residential with mechanical systems. ASHRAE standard 62.2 requires mechanical. There's a big issue with mechanical, whether it's exhaust or outdoor air ventilation, is they only work when they're on. And there's questions of how they're controlled and how they're operated. The standards, the building regulations just require that they be there and that they be capable of moving a certain amount of air. There's no requirement that they're actually operated. So if they're noisy or something, or the occupant isn't aware, it may never get turned on. In commercial buildings in this country, they almost all have mechanical systems like that kind of H system that I showed with the air coming in and some recirculation and air pulled out from the space. That's pretty common in commercial buildings almost all the time. There are other types of systems, a whole host of other systems. That's a longer discussion. A lot of schools will have fan coil units, little through-the-wall units that have a little vent that's all clogged with grass clippings from outside and has never had a filter change and moves a little bit of air past the coil. It'll recirculate some air and hopefully pull a little outdoor air. Almost all commercial buildings will have a serious bathroom exhaust that actually runs. And that's kind of the short answer to that. But there's a lot of variation. We'll talk about that a little bit. And I see the time is rushing on, so I'm not going to get into this a little bit. This is a loaded question, this last one. How much effort should you put into measuring ventilation in their air quality studies? There are a lot of measurements of pollutant levels in buildings where they sort of gloss over ventilation. And I don't know how you interpret an indoor concentration without knowing something about the ventilation. Or, and I haven't looked lately, definitely in the past, there would be a reported ventilation rate and they would never tell you how they measured it. If somebody wrote a paper where they measured, the levels of 20 different individual volatile organic compounds and never told you how you measured it, that would be unacceptable, I hope. But somehow, ventilation, kind of gets a pass that it doesn't deserve. The best way to measure ventilation in the building, it depends on why you're doing it, the configuration of the building, the type of system. This is a question that I could answer, but I got to sit down with you. We got to draw some pictures and talk about your building and how it's laid out and which rooms you're interested in and what type of systems. So I won't answer that second question standing up anymore. It's a discussion. And I'd be happy to have that discussion with any of you as the week goes on. There's somebody, I forget who it is, that I'm meeting here, because she and her advisor measured ventilation in some school classrooms 3 different ways and got 3 significantly different answers. And I don't know why, but maybe we can figure out why that happened. So I'm going to talk about 5 important, I think they're important things. First being how ventilation rates vary with weather and other effects. The second is using occupant-generated carbon dioxide to estimate ventilation rates. This whole question of reporting ventilation rates in IAQ studies that I mentioned. A little bit about ventilation efficiency and air distribution in the room, but not very much. And then what the standards say. So I've got about a half an hour to cover these. I can't remember how much time I allotted, so we'll find out how it goes. So, so the first one is how do ventilation rates vary with weather? I'm going to show you some data, and I'm going to make the point that if you measure the ventilation rate once, I don't know what you learn. Cross your fingers, because hopefully you measure it right. But it only tells you, at best, the ventilation rate under those conditions. And tomorrow it may be windier, and it's going to be different. Tomorrow it may be colder, and it may be different. So if you really want to understand the ventilation characteristics of a building, you have to measure it a lot under different weather conditions, different modes of system operation. I mean, fan on and fan off, let alone how the fan is operated and how the outdoor air intake dampers are modulated. So it takes a lot of measurements. That single value, again, may be wrong, so at least you want to measure it a few times to convince yourself there's some consistency in the result. But if you really want to understand the ventilation characteristics of the building, you need to measure it a lot of time. And now, you may not have the budget for it, but I don't want to hear about that. But, if you really want to understand, you got to make multiple measurements. Maybe you only want the ventilation rate during your pollutant concentration measurement. That's all you really care about. You don't care about what it was a week ago. And that's fine, but it's probably still a good idea to repeat it, to convince under the same conditions, to convince yourself that that measurement made, that ventilation rate that you measured when you were measuring this, volatile organic compound, is a reliable measurement rather than measuring it just once. So they vary. One value, I'm not sure what it tells you. If you really want to understand, the airflow characteristics of the building, you have to measure it a lot, which is tough. So here's one study. One of my first slides made the point that all this stuff is in a 2016 paper in Indoor Air. So you'll see that on one of the early slides. So you can, pretty much all this stuff is in there, one form or another. So here's a paper that Lance Wallace and a few other people did a study of an occupied townhouse and made about 4,600 individual tracer gas decay measurements. Lance Wallace, anyone ever hear him? He's kind of like a grandfather of indoor air quality to a large degree. He's still doing it. He's an amazing guy. So here is a distribution, log distribution of air change rates in that building, and just over 4,600 measurements, and it's a log normal distribution, meaning there's a predominance of lower air change rates. And here are the air change rates plotted against the indoor-outdoor temperature difference. So, when it's colder outside, the air change rate is higher, which is what you expect. This has been known for decades, but it hasn't been measured in a lot of buildings. This is just under 200 measurements. I think this data we screened out the high wind speed stuff, because that would have, complicated things. You had an even higher rate above the line. And, that fit pretty well. And so this is not a particularly novel result, but it took a lot of data to get this. So air change varies quite a bit on the left, and it varies directly with temperature difference. And if we had a separate plot against wind speed, you'll see that it varies with wind speed, which you're going to see on the next slide. So here's another study of a test house that we have on our campus that we've used for looking at air cleaners and generator, carbon monoxide levels when you run a generator inside. We're still doing some tests like that. Not a smart thing to do, and if you ever do it for research purposes, be really careful. Because if you run a generator inside this house, or any house, you will hit fatal levels of CO in hours, if not minutes. So people do it, unfortunately. And they're not careful when they do it. So this is a house where we did a retrofit study. We got the house, we measured the leakage, we measured infiltration, and then we tightened up the house. We took the siding off and wrapped it in a house wrap, and we tightened all the ducts in the crawl space. And these are the air change rates versus temperature difference before the tightening and after. So you see more so before, a pretty strong dependence on delta T, not as strong as some, because it had to do with the fan running. The fan had ductwork in the crawl space, and it leaked, and it's a complicated dependence. It's really kind of a weird pattern, but we convinced ourselves in a physical sense. And this is after the retrofit. The air change rates went down. A cleaner, I'll call it a cleaner dependence on delta T. But this took a lot of measurements. This is a plot of, air change rate versus wind speed. I'm sure it's right in the paper. It's delta T down here. And you see that, this may be wrong. This is terrible. This is with, that's with the fan on, and remembering, no, this is with the fan off. Okay? This wind speed is wrong. This should be temperature difference. Before the retrofit, a nice straight line, dependence on delta T, an indoor-outdoor temperature difference. After the retrofit, the rates go down, the slope flattens out a little bit. Yeah?
If fan is off in the second graph, then it's only infiltration, right?
This is just infiltration. This house had a mechanical ventilation system, but we turned it off for these tests.
So I just noticed compared to the first graph, when the fan is on and at the same temperature difference, it seems like the fan is not making a big difference in air change rates because they're almost the same, the numbers.
Yeah, though, you look out here where it's hot outside. Well, we don't have a lot of data where it's hot outside. But even at zero, we're getting about 0.1 air change an hour with the fan off. And before, we were getting 0.4. And that's because this system, while it brought no outdoor air into the building, it had a duct system for the recirculation system that ran through the crawl space and leaked a lot. So when it would leak in the crawl space, it would change the pressure inside the house and induce more infiltration into the house. And you don't see that when it's off, but you see it when it's on. And that was a really weird pattern.
Yeah, after the retrofit, if we just focus on the blue dots and the rest, when the temperature difference is 10 degrees Celsius, the air change rate is almost the same.
Right. After the retrofit, where we tighten up the ducts, and we tighten up the floor, and if there's more construction details I can get into, we have much more similar fan on and fan off. Good observation. So here, there's some more data showing, the variation in weather dependence. And measuring one air change rate in this house would just tell you, what it was, right there. And if that's all you need to understand your contaminant concentration measurements, maybe you're fine. But if you want to understand what's going on in this house, you need to make a lot of measurements. And when somebody tells me that the air change rate of the house we're studying is a half an air change an hour, I don't know what that means either. Under what conditions, when did you measure it? Did you measure it once? Did you measure it, was that a heating season average? Was it on the, the one day in the year that we could get into the house? But it doesn't tell you anything all by itself. You got to tell me something about the conditions.
Sorry, just to follow up on that, at 25 degrees, why is with the fan off, which is the one on the right,
Right.
why is the air change rate
It's
higher
higher.
than when the fan is off?
So it's about,
About
0.3, 0.4, 20.
Compared to like point.
And here, it's a little bit lower. It's because the residual leakage into the crawl space kind of changed the pressure. I could draw you a picture some other time. It kind of pressurized the bottom of the building where when it's cold outside, usually the bottom of the building is depressurized. So,
Because of the temperature?
yeah, I'll draw you a picture. It's kind of weird. But another good observation. So the second topic I wanted to talk about is using occupant-generated carbon dioxide to estimate ventilation rates per person. This is real common. It's poorly understood and abused. You know, so that's bad, right, to be poorly understood and abused. But people do it all the time. They measure the CO2 level. They do some math without understanding where the math came from, and they walk away with an outdoor air change rate per person. In reality, you know, when you do this, you're just using CO2 as a tracer gas. I measured the ASTM, I mentioned the ASTM standard. There's the ISO tracer standard. There's a little completeness. And all you're doing is you're taking you're using CO2 as a tracer gas, and it's a convenient tracer gas because we have a free injection method. Well, they're not free. You know, you have you're paying to be here. You're not a free injection measure. You had to pay money to inject CO2 into this room. But you have a convenient injection mechanism for people. So they're injecting tracer gas. If this was a room all by itself and there was no other part of the building, you could take this room, you know, do the mass balance, and you could solve the mass balance equation, and you would get the ventilation rate is the rate at which we generate CO2 divided by the steady state concentration minus the outdoor concentration. And we don't need to go into all this details, but it's real convenient. You know, the generation rate depends on us. You know, how big we are, how active we are. You know, I'm more active than you are, definitely more active than that person who's back, who's nodding off. But this depends on the people, the generation rate. And then the steady state level, you know, this is a steady state solution to the mass balance equation, which is great. It's especially great if you're at steady state. So when we came in this morning, the concentration of CO2 in this room was basically the outdoor level. And then we came in and it started going up. If I knew the air change rate of this building, I could tell you now, an hour later, are we at steady state or not? I don't know. You have to measure it. You'd have to know something about the ventilation system. If you get the steady state, this equation is great. You can use it. But I've already said, these are all the assumptions behind it. It's a single zone with a uniform concentration, that the ventilation rate and the generation rate are constant. The ventilation rate and the outdoor concentration are constant, and that the generation rate is constant, the occupancy is constant. This is tough. In an office building, it might take 6 hours to reach steady state, which, you know, it's unusual to have an office building occupied constantly for 6 hours because people go to lunch. They leave the building. And that, I should say the concentration is steady state, equilibrium is a different term. There is an ASTM standard on how to do this. So people who do these measurements should know what they're doing. People doing any measurement should know what they're doing, right? Have people use this approach? I mean, there's nothing wrong with it if you understand it, right? And consider the assumptions, which is true about lots of things. But this is one of those issues I used to get upset about, but I don't get upset about it so much anymore. Because I have a quota. I can only get upset about 5 issues at any given time. And this has moved off the table, and I've got 5 other issues. But I don't get as upset as I used to. So, yeah, I used to get upset about this, was people doing indoor air quality studies, indoor pollutant studies, and not telling, and giving ventilation rates, but not telling you how they measured it. So, you know, that has been a problem. I don't know how you interpret indoor contaminant levels without a ventilation rate, or how you compare, you know, interpret the concentrations yesterday to the concentrations today without knowing the ventilation rate, unless you're really confident it was the same on both days. And how do you compare studies in different buildings? You know, this contaminant is higher in this house than that house. Well, is it the source? Is it the ventilation? Or what is it? So it's an important parameter. So, you know, some of the things you need to think about and report are, tell me something about the building and the systems in the building, and then do the measurements. And this is a much longer discussion, but I just have a couple of slides with some of the parameters you need to think about to understand and when you're evaluating ventilation. So there's building characteristics up there, a whole list that I will not go into, but and I won't read, because that'd be really tedious. You're going to learn that tomorrow in effective presentations. Don't read your slides. Okay? But I will say, you know, when you look at the building configuration, don't just look at the rooms where the people are. You know, look at the shaft, look at the elevator. Think about the elevator shafts and stairwell shafts. Think about all the air volumes. Buildings have lots of obscure spaces that you don't see unless you look for them. You know, plumbing chases that might run from the basement to the attic. You know, it's a direct connection between all the floors, crawl spaces, attics. You know, I have a great picture, not here, of a mother raccoon and her babies who lived on the ceiling of our basement bathroom for a couple days till we chased them away without any injury to the raccoon. You know, the air will find those spaces. You know, you might not know they're there without thinking about it. So all the air volumes are important. And then the ventilation system. What information do you need to think about? What information do you need to report? How is the building being ventilated? Infiltration, natural or mechanical? In answer to the earlier question, hybrid systems. There are more and more commercial buildings that have both natural and mechanical. There's a hybrid system, and it might be when natural weather forces aren't adequate to get the air it needs, it kicks on a fan. That's basically what a hybrid system is. And if you have a system like that, where are the openings? How big are they? You know, how is the air moving? If you have a mechanical system, how much air is it intended to move? And how is it controlled? And what type of filters do you have? Oh gosh, I'm reading the slides. I'm sorry. And then there's other systems you care about in the building. You know, how is it heated and cooled, and so on. So those are just some of the parameters that we care about. And yeah, man, I gotta hurry up. And then ventilation performance. I think I mentioned all of these parameters already. So there's the airflow rates, air distribution and ventilation efficiency. We'll talk about that in a minute. That's just characterizing the airflow patterns within the spaces. And also, you know, there's upstairs, there's an air handler serving lots of rooms. And it's intended to give a certain amount of air to this room, a certain amount of air to that room, a certain amount of air to the other room. Is it actually doing that? Is it actually distributing the air the way it's intended to? So that's what I mean by air distribution. Building air tightness I talked about, and pressure differences can be really useful to understand airflow in a building. You might not be able to measure all the airflows, but pressure differences are much more straightforward to measure with some relatively inexpensive handheld devices. You know, is the building at a positive pressure or negative pressure outside? What about air zone pressures? Are the bathrooms at a lower pressure than the hallway? I sure hope so. You know, you want air to move from a clean space to a dirty space. And you can, measuring that flow may be tough, but you can measure the pressure difference to verify that the dirty space is at a lower pressure than the adjacent space that in theory has cleaner air. So these are some of the measurements. And then I mentioned air distribution, and I'm not going to say a lot about it, but I have this video and I figured I'd put something in there that's kind of cool. I mentioned air distribution is how much air is the system distributing to the different rooms. That's in the design, if you can find the design. It's in the design. Is it actually putting, you know, 200 liters a second into this room and 150 liters a second into that room, whatever the specs were. Within the room, the airflow patterns have can be of interest and can be pretty darn important. You know, and this is simulating a contaminant in a room, and you know the variation within the room can matter a lot. If you're using a sensor to control something, you know, to control the ventilation rate or to detect a bad substance, to do something quickly to protect the occupants. It matters where you put that sensor, and so you can do this CFD, computational fluid dynamics analysis, to look at the detailed air velocity profiles in the room and the detailed contaminant profiles in the room. That's a whole nother realm that I'm really not going to do anything else, say anything else about today, but you got to see the cool video, so that's a good thing. And then standards. We talked a little bit about the standards that are on the books that have tables of ventilation rates for different space types. ASHRAE standard 62.1 is commercial or institutional buildings. 62.2 is residential. When I made this slide, it was only low-rise residential. Now it's all residential, including multifamily. There's a European standard that covers all buildings, and there are some good reports. AIVC is the Air Infiltration and Ventilation Center. It's a great resource for all sorts of information. If the country where you live is a member country, you can get it all for free. All these reports, conference proceedings, they've put together a compendium of international standards on ventilation. It's a great resource if you're interested in infiltration and ventilation and indoor air quality, so remember them. They have a conference every year. Met Giorgio in Nottingham last year, and this year, in September, they're meeting outside of Nice. So, got to go to that one. Important point is these are standards. They tell you how much air you need to bring in. It's important. They're used in the design of a building. But just because a ventilation rate is in the design doesn't mean it actually happens in the building, right? It might not be, it's an important first step, but the system may not have been installed properly, it might not have been commissioned properly, it might not be operated as intended, and as time goes on, sensors go out of calibration, dampers get sticky, and you may not achieve the desired, the intended building design performance any longer. So it's important to look at the design, but to bear in mind that the actual performance can be quite different. And here's an older study where we measured air change rates in a bunch of office buildings, several thousand measurements. They're all 1 hour decay rates, and here's the air change rate distribution. 0.2 air change an hour bins from 0 all the way up to economizer operation, which is a small fraction of the hours, but it's important for energy. I will note that of these measurements, almost half of them were below the ASHRAE standard that was in effect at the time, and about half of them were below what the design said they should have been. Okay, so systems were not being operated at the design level, and these rates include infiltration, which is probably, the actual intake is probably half of this, each of these numbers. So what the system was bringing in was well below the design value in the standard. And this is not uncommon, as I will show in the next slide, which is there was a study, an EPA-based study, which was done a number of years ago, where they went to 100 randomly selected office buildings in the United States and measured airborne contaminants. They did occupant surveys, they gathered building design information, they measured air change rates, probably measured a couple other things. 100 randomly selected office buildings. I think 3 or 4 of them were naturally ventilated. And each of these lines is the measured minimum outdoor air rate divided by the design. So if the system was being operated exactly as intended, all the numbers would be 1. Right? That would mean that the measured rate was the minimum value. And you can see quite a bit of variation is really the point here. Some of them are pretty darn low, the design value, and some of them are well above. Low is bad for air quality. And if you believe that the design number is the right number, the high ones mean that it's bad for energy. So, yeah, so that's another example of the, or demonstration of the fact that systems are not necessarily designed, not necessarily operating as designed. Another point in the base study, of the 100 buildings, they could only find the design documentation in half of them. It was just lost, or it was buried in somewhere in a basement mechanical room. So, you know, how do you determine if a building is being operated as it was intended if you can't find the design information? And I don't think that was unusual at all. But it's regrettable. So a few summary points. Terminology matters. If you're saying ventilation, you know, say outdoor air ventilation, say supply air ventilation, be a little clearer. It takes longer, but it's worth the extra time. Ventilation rate, outdoor air ventilation rates depend on weather, depend on system operation. A single number without any indication of what was going on at the time is not, it doesn't tell you a lot. You know, I didn't see a lot of people raising their hand when I talked about this, but if you're using occupant-generated CO2 to estimate ventilation, you're doing a tracer gas measurement. And look at the assumptions that go along with that measurement and think about whether they're valid. And then finally, buildings aren't necessarily ventilated as intended because of installation issues, operation issues, maintenance issues. And any final questions before you get your free lunch that you paid for? Last question.
Sure. Strategies are, I guess, tips for measuring ventilation rates in large-scale buildings where we want to minimize disruptions and routine activities, so it may not be logical to blow door test a facility with 100 workers. You know, so just any tips you have outside of kind of what you covered already.
I mean, fortunately, you can do the pressurization test at night when there's no people there. You know, the decay test you can do during normal occupancy. You kind of want to measure the air change rate when things are operating normally, because if there's no people in there, you don't have loads in the thermal loads in the space, and the system isn't going to operate in a typical manner. You know, they're going to have to get it cleared by the building owner and maybe their health and safety people, and that's a longer discussion. We could be happy to talk about that. And so there's a partial non-answer. I look forward to talking with you as the conference goes on. Anything else?
I have a question, because ventilation rate really matters a lot depending on weather and wind speed. So when designing the system for a building, what conditions should we use?
The question was, you know, since infiltration rates vary with weather, what do you do when you design a building? If you look at the guides for calculating loads, like in the ASHRAE handbooks and so on, they do a really bad job dealing with infiltration loads for estimating. You know, most of the loads are calculated on a design day, you know, which is like a really cold day. I don't think they necessarily consider the wind speed on that day. Yeah, I've never been asked that question. That's a really good question. I don't want to just blurt out an answer and give all of you erroneous information. I'm going to think about that and talk more. So I'm going to be here all week. I'm going to be here over the weekend, but I'm going to be here all week, and I'd love to chat with some of you about what you're doing, as well as answer some additional questions. And then I have this great picture. This is actually an old wind tunnel that was at the National Bureau of Standards many, many decades ago. And this is in the public domain, this photograph, and that was actually the controller, you know, for the wind tunnel. So I hope that you have a good week of ventilation and air quality and learning and interacting, and thank you very much for your time and attention.
All right, thank you for that great presentation. It's lunch now. It's going to be outside, right outside. And we'll come back at 1.